Okay, so this is for 2.3, and I'm actually gonna skip 12 for this one. As you can see, there's 74 problems here, so I'm gonna do the first one and then 13 and then 25 and so forth. Let me open with note about functions. So a relation is any set of ordered pairs. So you could write, rainbow, tree, flower, fly, leprechaun, fly as well, gold, silver, XY, 2, 4, 9, 3 halves. Any set of ordered pairs is a relation. And sometimes we draw these instead of writing them as a set like this. We can define them by definition. We can say x squared equals y squared. And then all solutions to this are a relation. You have 2, -2, -1, 1, 7, -7, 8, 8, and so forth. That's a relation. Sometimes we will just say, okay, well, it's a mapping, and it goes like this. And in a relation, it can also go like this. So you can have C going to 3 different places. There are kind of no restrictions. It's just ordered pairs. Any list of ordered pairs, any way of describing a list of ordered pairs, infinitely many, finitely many, however many you want, in whatever way that you want. The thing that makes a relation a function is that you can't have this splitting over here. So I like to think of it as though, since we often draw mappings with these arrows, you have your domain over here, and you have your range over here, and you have points in there. And the function goes this way. So f takes that arrow there. It takes this one here. Of course, you've seen plenty of functions that, f of 1, say, x squared. F of 2 is 4. F of -2 is also 4. So they can both land the same place. But any specific x only gets one arrow. So imagine that it's a competition and everybody only gets to shoot one arrow. So two people's arrow may hit exactly the same place, but nobody can shoot more than one arrow. If they do, it's not a function, it's just a relation. So coming back over here, this relation is write a set of ordered pairs that defines this relation, write the domain, and then write the range. So domain and range work the same way with a relation as they do with a function. The set of first elements is the domain, the set of second elements is the range. And then we're trying to determine if this is a function. So Jack Nicholson goes to 12 because that's how many Oscar nominations he's received. So 12 goes there. Dustin Hoffman has gotten 7, so he gets 7. Sean Penn has gotten 5, and Al Pacino has gotten 8. Now, to determine whether or not it's a function, we just have to decide if any one of them might have had 2 results. So is it possible that Jack Nicholson has had 12 Oscar nominations, but has also had 8 Oscar nominations? Well, no, he's either had 12 or he's had another number, but there's not more than one option for the answer. Say, how many Oscar nominations has Jack Nicholson gotten? There's just one answer. So if there's just one result for the guy in the first coordinate, then it's a function. So oh, the domain is the list of all the guys. The range is 12, 7, 5, 8. And then it is a function. If it had gone the other way and you had the number of Oscar nominations and you had to pick the person, it's possible that someone else got 12 Oscar nominations, or 7 or 5 or 8. So we wouldn't know for sure that it was Jack Nicholson, Dustin Hoffman, Sean Penn, and Al Pacino we were looking at, and then we would have had to say no. Okay, so now I'm going to go over to 13. We're trying to decide if this defines a function. -3 goes to all 4 of these values. So if -3 is in a competition, even though that appears to be the only person who showed up for it, they're still cheating by using all these different arrows, so it is not a function. Okay, so here we want to plug in. So you see that it says h and then it has parentheses and it says x. What that means is x is the variable. So it will indicate where you put the value that's in the parentheses. So whatever goes in the parentheses, you put where the x was. So in this case, we have the 3 is just a 3. The x is replaced by 7. And that's all you do is put the 7 where you saw the x. Sometimes the x shows up in a lot more places, takes a little bit longer, and there's reductions and simplifications, but in this case, put it in there, and that's it. 37. Okay, so this one's a little more complicated. So let me give us some space to work here. Here. Okay, so I'm still going to put just c minus 1 wherever x was, just like I would if it was 7. So f of c minus 1 equals whatever's in the parentheses squared plus 2 times whatever's in the parentheses, because that's what f does to x. It squares it and then it adds 2 of it. So c minus 1 squared plus 2 times c minus 1. Now I'm going to FOIL this. You can FOIL it all the way out if you want. You'll end up with c squared minus c plus 1. And I'm going to distribute that 2. Now I want to collect like terms. C squared minus 2c plus 2c, those cancel. Plus 1 minus 2 is minus 1. So c squared minus 1. Whoops. Minus 1. $49. Okay, so we want to find the x and y intercepts. An x-intercept is where you cross the x-axis, which means that y is 0. The y-intercept is where you cross the y-axis, which means x is 0. So in this case, this is function notation. The function is what is normally labeled y. Okay, so as far as the y-intercept, there will only ever be one if it's a function of x, because x being 0 can only have one y. So I'm going to say y is root x minus 4. r of x being root x minus 4 might indicate to you that it's some sort of radius, or, you know, for, I don't know what x would be in that case. It could mean something. They could have chosen r for a reason if this was an application problem. It also indicates it is a function. Y is not necessarily a function, but r of x is a function. That notation tells you that it is, but I'm just going to rewrite it to help us with the intercept. So for the y-intercept, x is 0. So y equals root times 0, root of 0, sorry, minus 4 is negative 4. For the x-intercept, y is 0. So 0 is root x minus 4. So root x equals 4. That's moving the 4 over and then writing them in the reverse order. So then I square it, and x is 16. So it only has one of each. So the x-intercept is 16, 0. And the y-intercept is 0, negative 4. Okay, so here we want the domain. When we get to logarithms, you'll have a new domain restriction, but at the moment, you only have 2. If you have some fraction, then what's on the bottom cannot be 0. That's a domain restriction. If you have a root that's even, then whatever's under it has to be at least 0. So these are the only 2 things at the moment that you all have to worry about. So in our case, we have a root. Nothing's there, so it's an implied 2. So that's even. So we need x plus 2 to be bigger than or equal to 0, because it's just whatever's under there, bigger than or equal to 0. Move over the 2. And this is, if you wrote it like this, that is the domain, but it asks for it in interval notation. So we need to write it in terms of an interval. So let me first do a number line. And you don't have to do that. If this is clear to you, it's fine. If you know what to do from here, but I'm going to pick a test point on either side and check, is negative 4 bigger than or equal to negative 2? It is not. Is 0 bigger than or equal to negative 2? Yes, it is. Because of the equal sign, we include the negative 2. We go this way. So negative 2 and going off to infinity. And that's how to write it in interval notation. You never put a closed bracket on infinity because it's not a number, so you can't include it. And then 73. So we have a square with sides of length 4x, diagonals of length d, perimeter P, area A. So we want P as a function of x. It's the perimeter. Take these separately so they take up less space. Okay, so the perimeter is the measure around. So 4x plus 4x plus 4x plus 4x. So I have altogether 4, 8, 12, 16 x's. Area is length times width. Area as a function of p is a side is 1/4 of p. So it's 1/16 of p squared. You might have been tempted to say, oh, it's p times x, but then it's a function of p and x, and you want it just p. Okay? And then we want p as a function of a. So because a is the side squared, the square root of a is a single side, and p is 4 of those. D as a function of x. So in a square, when you have a 45, 45, 90, this relationship is a 1, 1 root 2. Pythagoras would give you that actually, so you could say 4x squared plus 4x squared is d squared. That's just the Pythagorean theorem. So 16x squared plus 16x squared is d squared. 32x squared is d squared. We want d as a function of x, so d is square root of 32x squared, which you can take out 4x and say it's 4x times root 2. Normally with all these roots running around, you'd have to worry about plus and minus, but these are all measures of positive lengths, so we don't have to do that. I'm just leaving this up to make our lives a little bit simpler on the next one. Now I want to solve for x instead, so I'm going to take d and divide by 4 root 2. And then p as a function of d. P, remember, was 16x, so that's 16. I'm substituting now for x. 16 over 4 is 4, and this is 2 root 2 because it's 2 times 2 over root 2. 2 over root 2 is root 2 by definition. I meant times here, not equals to. It's strange. So P is 2 root 2 D. And A was 16x squared is 16 times d over 4 root 2 squared and that kind of tediously wraps up this section.